This presentation is meant to complement John Conrad's book, Resource Economics, 2nd edition. It is meant to look at dynamic optimization using discrete time. 3 approaches are going to be used: the Hamiltonian, the Lagrangian, and dynamic programming. And we're going to show from the Lagrangian how you can get to the Hamiltonian and thereby to dynamic programming. We're going to look at the resource management problem in discrete time. We're going to look at maximizing the returns to the harvest of fish or to the harvest of a wildlife species such as duck, elk, or moose over time, subject to the constraint that the wildlife stock is a function of growth and what is then harvested. The state variable will be the fish stock or the wildlife stock, where fish are measured in terms of kilograms or some other measure of mass, and the wildlife stock is measured in terms of individuals. The control variable or the decision variable is denoted by U, and what it refers to is the amount of effort that is expended, for example, by fishermen when they're fishing, or by hunters. It's going to be the number of individuals that are harvested, number of moose taken, or elk that are shot. The problem can be specified as follows. It's the discounted sum of net returns, where R refers to the net returns, and these are a function at any given period of time of the state variable, in other words, how many fish are actually in the ocean, or the number of individual wildlife that are available, number of moose, let's say, in a particular region, and the control variable U, the moose that are shot, or the amount of fish taken, or pardon me, the effort in taking fish. And we're going to discount the net returns in any given year or any given period by this parameter, the discount parameter, beta t. And beta is 1 divided by 1 plus R, where R is the social rate of discount, or perhaps the discount rate that the manager is using. So this expression, this first expression, tells us that we're going to be determining the optimal harvest, or the optimal amount of effort that we're going to expend in each period. And we start with the current period, which we denote here as t equal 0. And the end or terminal period is going to be big T. So T is going to go from 0 all the way to big T. At time big T, we have a salvage value, and that salvage value is given here. That is the value of the wildlife stock, given that you know the number of wildlife that are still out in nature, or it's the amount of fish that are still available. For example, in the case of the Atlantic cod fishery, where there are really no fish available anymore, the salvage value would be essentially 0. And of course we discount that salvage value as well by beta capital T. Now, the problem that we're looking at begins with a transversality condition, an initial condition where x0, the stock of fish or the number of individuals in the wildlife species, is given. And here we're going to denote that by x bar. The equation of motion is this one here, which tells us how the stock changes from one period to the next. And that change, which in the continuous time model is denoted by x dot, which is simply dx dt, that change is a function of how much stock there is to begin with and the amount of effort or number of individuals taken. So we'll come up with a simpler expression for that a little later on. Now we can form the Lagrangian, and you'll notice that the first part of the Lagrangian, up to this term here, is basically you're repeating that objective function in the previous slide. The next term deals with that first initial condition. So we have a Lagrange multiplier, which we denote x sub 0, and we take, remember that equation was x naught equals x bar, and now we've got x bar on the left, and we subtract x naught, and we've got a positive lambda 0. We're going to do that for the other time periods as well. And that's what the remainder of that expression has. Okay, notice that that expression has each of these equations of motion given by xt plus 1 minus xt, and notice here that the sign is changed because it's on the right, and this is the right hand side of the equation of motion. And notice that this Lagrange multiplier is given by lambda t plus 1, referring to this xt plus 1, which is the first term in that equation of motion. All right. Now we take the first order conditions, and when we take the first order conditions with respect to the control variable, we refer to that as the maximum principle. So we take the first derivative of that function dl, of the Lagrangian with respect to the first control variable, which is found right here. Okay, and that control variable is at time t0, and it's given by that 0 right there. So we get beta 0, because remember t is 0, times the partial of r with respect to the u0 plus beta 1. All right, the beta 1 comes here. Right there is where the beta 1 is, because you put in a t equals 0 and you get beta 0 plus 1. You get the beta 1 here. Times, and you do the same thing with that lambda, because you've got a t equal 0 right there, and you've got the 1. So it's a beta 1, a lambda 1 right here. And then the partial of f with regards to u0, and we set that equal to 0. And we do the same thing for each year up to year t minus 1. So at t minus 1 we get this expression here. And notice that we get a beta t minus 1, and we get a beta t here and a lambda t. And where does that come from? Well, think of it. Put in big t minus 1 into that expression, and you get beta t minus 1. If you do it over here, you get the beta t. If you go over here to this last term, which I've circled, you get the beta t plus 1. Again, you're putting it in a big T minus 1 plus 1, which gives you big T. That gives you that beta T here. And you do the same thing with this lambda T. You've got lambda big T minus 1 plus 1 gives you lambda big T. All right? And then the partial of f with respect to u subscript big T minus 1. The co-state equations, notice that we're calling these the co-state equations, are the ones where you take the derivative with respect to the state variable. All right, and there's a state variable in every period up to and including in this case. Now in the previous case, you'll notice that no decision is taken in the tth period, because you don't have a u subscript big T. But here you're looking at each of the state variables, and they run from x0 all the way down to xt. Whereas the decisions are made, they run from u0 to ut minus 1. All right. So now we're taking the co-state equations, we're taking derivatives with respect to the various x's, and this gives you the results. Okay. And notice that in each case here, there are two terms, a beta 2, beta 3 here if time is 2, a beta 1, and a beta 2 if the time is 1. And the same thing with regards to these lambdas. All right. We get the same kind of a result, that if t is 2, then we get a lambda 2, and if t is 2, you get a lambda 3 in the expression as well. And these expressions are all set equal to 0. And again, we have one last expression in this case, because of this xt here, we have this salvage condition. And the salvage condition basically states that you've got this result here, that the Lagrange multiplier at time t is the first derivative of the value, the salvage value, divided by, or the first derivative with respect to that x. Okay, then we look at the state equations, which basically give you back the equations of motion. And you see that we take the derivatives again with regards to lambda 0 all the way down to lambda t. We take each of those derivatives. This gives us the initial condition again, and each of these gives us the various conditions for an optimum, and each of these is the equation of motion. Okay, you'll notice that what we've recovered here are these equations of motion. Okay, so we can summarize the foregoing conditions by, as you see, taking the partial vel with respect to ut and setting them all equal to 0, and then we get this generalized expression once we've rearranged it, which gives us this one. Okay, and we note that it's for all t from 0 to t minus 1. Then we can do the same thing when we've taken the derivatives of the state with respect to the state variable. So these are the co-state equations. All right, so 2 is the co-state equations, 1 is the Mach's principle, so this is the Mach's principle, and these are the co-state equations, and these are the state equations back. Once we've rearranged everything, then you see that these are the general forms. And these last two equations, as I noted before, are the transversality or endpoint conditions. The first equation, number 4, is the initial condition, and the final equation is your endpoint condition. Now, let's look at the discrete time Hamiltonian. We're going to do it first by ignoring discounting. So we're going to say no discounting. And notice that we're going to go from t0 to infinity, just to simplify things a little bit. So now there's no salvage value term at the end, so there's nothing here. And we're just maximizing the net returns over time. All right, not discounted. We have again this same condition, the same equation of motion, and we have this initial condition that we know what the stock of fish is for the wildlife population at the beginning of time. Now, if we do the Lagrangian, this is the Lagrangian expression here. Okay, and we can take the first order conditions as normal. All right, and in this case we take the general conditions and we solve, we provided a more general equation here, and down here these are your equations of motion again. So equations of motion. Yep, for some reason I was erasing. Equation of motion. And this, of course, is our Mach's principle. Pardon me, it's our Mach's principle. Okay, the maximum principle refers to the first derivative of the Lagrangian with respect to the control variable, and that you set equal to 0. Now again, notice here that that when you're taking derivatives with the Lagrangian, okay, you have to be very careful, because in all of these expressions you have a lambda t and a t plus term. For example, you write the equations of motion like this: t plus 1 minus, it's xt minus x is a function of x at time t and u at time t. But you also have an equation that looks like this. Xt minus xt minus 1 equals f xt minus 1 ut minus 1. And what happens is, in this Lagrangian expression, you find all of those. So your first term will be r x naught u naught plus lambda 1 x naught rather, plus f of x naught u naught minus x1. Then you've got your next term in this expression is plus, and then you repeat this thing, but now with t equals 1, you get rx1 u1, lambda 2 x1 f of x1 u1 minus x2. All right. So you have to be careful that you're always catching two of these terms, except for the first equation here. Okay. Except for this first equation, you're catching two terms in all these cases. Okay. You're catching an xt term, a lambda t term, and a lambda t plus 1 term, which gives you that expression again. In the steady state, and this is the way we solve these problems, we solve the steady state, we find that the partial of r with respect to ut, pardon me, we've just taken, so what we're doing here is we're looking at each of these expressions and we're taking out the t, all of the t's. Okay? So we're taking out all of these t's and we get these expressions here. So remember, if we have, in this one for example, you get xt plus 1 minus xt was equal to f, but if xt and xt plus 1 are identical, in other words in the steady state they are, that term becomes, it goes to 0. So that's what's happening there. We then define, okay, and that's the key, we define the Hamiltonian as being h as a function of xt, ut, lambda t plus 1 t is equivalent to this first term, r, the net return, r is a function of xt, ut, and t, plus lambda t plus 1, f of x, t plus ut. So notice that when we go back to the Hamiltonian, all right, this is the Hamiltonian, we're taking this part and we're taking, if we go back, this lambda t plus this part. These two parts we're taking in this expression here, all right, and we form the Hamiltonian. And notice also that we have no longer got the summation in there. So what the Lagrangian looks like, if we make that substitution for the Hamiltonian, that's what that Lagrangian looks like. It's a Hamiltonian minus lambda t plus 1 xt plus 1 minus xt. So notice that we now have this Hamiltonian expression. So this expression here is the one we're going to take the derivatives with respect to. All right, so if we look at that, if we take the partial of L with respect to ut, we find that it's the same as the partial of h with respect to ut, and it's equal to 0, which implies that the first condition is that one. Okay, the h, the ut equals 0. And you can look at that by taking the first derivative of the Lagrangian in this lowest expression here, dh, the ut, first partial of L with respect to ut, and there's nothing here that has a ut in it, so then it's partial of L with respect to ut is simply the same as partial of h with respect to ut, and we set that equal to 0. And we do the same thing, all right, with respect to the co-state equation. We take the first derivative of that Lagrangian, and that's equal to the first derivative of the Hamiltonian with respect to xt, plus these two things here. If you go back again, you'll notice that you're taking, with respect to xt, you have each of these, you've got a lambda t plus 1 because you have an xt there, but you also have an xt minus 1, an xt in the previous expression, because remember, here's what you've got. You're summing over that, so that you've got this whole string of terms. So you end up with this expression here once you've cleared things up, and this is now your costate expression. And then the final one is you take the derivative of the Lagrangian with respect to lambda t plus 1, which is the same as taking the derivative of the Hamiltonian with respect to lambda t plus 1, minus xt plus 1 plus xt equals 0, and that gives us this expression here. So if you're looking at the Hamiltonian, you have to, it's probably best to just memorize these three expressions, all right, although you can derive them very simply. Now, when we look at the steady state, we have xt plus 1 is equal to xt equals x, lambda t plus 1 equals lambda t equals lambda. And what we then find is this here, okay? We find that dh du equals 0, dh dx is 0, and dh d lambda equals 0. So in the end, what we end up with is these three expressions can be solved for the steady state solution. And that's the way we often solve these kinds of problems. Okay, now we were interested in discounting, and when we maximize the expression where we include this discount factor, then everything else is the same. We find that the Lagrangian is given by this, okay? And now what we're going to do is we're going to look at the first order conditions, but with discounting. So this is the first order condition with respect to setting the Lagrangian with respect to ut equal to 0. Notice that that beta t and the beta t plus 1 will cancel out, so you've only got this beta left. And this is the expression that you get. So what is this called again? Well, this is the maximum principle. Max principle. View. If you then take the costate equation and you find that, you again get this expression beta t followed throughout the left-hand side, in which we then get rid of, and we end up with this result here. All right, and this is our costate equation. And finally, we get the equations of motion back right here. So, in a steady state, where we set everything, all the t's equal to each other, then we get three expressions, the first one being the maximum principle, the costate equation, and we get the equations of motion back as well. However, we make a slight adjustment and we define a current value Hamiltonian as this expression here plus beta times lambda t plus 1 f of x t ut. Now what we're going to do is we're going to combine this and we'll refer to it as some other kind of, we might use, say, phi t plus 1 to refer to the discounted Lagrange multiplier. In practice, however, they often don't use the phi t plus 1, but just keep a lambda t plus 1 there, or lambda instead of phi. And people will know that if you're talking about the current value Hamiltonian, that you're dealing with a discounted Lagrange multiplier. In this case, the Lagrangian is defined like we show here. And I've lost my pen, it seems like. Note that we have a current value Hamiltonian, so the shadow price is a discounted shadow price. Now, the first order conditions are, again, this is your max principle. dl dut is equal to dh dut equals 0, so we find the partial of h with respect to the control or decision variable we set equal to 0. That's our maximum principle. The second one gives us the co-state equation, and notice that that expression is given by beta lambda t plus 1 minus lambda t equals minus the partial of the Hamiltonian with respect to xt. And finally, we get back the equations of motion, which we find as xt plus 1 minus xt equals, and then on the right-hand side, the partial of h with respect to lambda t plus 1. Again, in the steady state, we get the three equations back. Partial of h with respect to u equals 0. The negative of the partial of h with respect to the state variable is equal to beta lambda minus lambda, and the partial of h with respect to lambda equals 0. That gives us the steady state. So in many of these problems, rather than looking simply at the path from one condition to another, we try to find the steady state solution, and that will tell us how much effort we should put in or how many animals we should harvest in any given period of time. And it will also give us the net return that we can expect to get. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.